The movement travels down the spring, and when it reaches the other end, it bounces back. It's reflected.
Notice that when the slinky wave is reflected from a fixed end, it reflects back on the opposite side. Notice the different parts of a longitudinal wave. Rarefaction is where the individual coils are far apart, and compression is where the coils are close together. If the angle of incidence is 0, then the angle of reflection is 0. If the angle of incidence is 35, then the angle of reflection is 35. If the angle of incidence is 45, then the angle of reflection is 45. If the angle of incidence is 55, then the angle of reflection is 55. Each portion of wave front obeys the law of reflection.
All parts of the wave strike the barrier and are reflected to the center. If a circular wave starts at one focal point of an ellipse, it will converge at the other. This circular wave did not start at one focal point of the ellipse. Notice the reflected waves. As the source is moved nearer a focal point, the reflected waves more nearly converge at the other. This circular wave is generated at one focal point and converges to the other. Circular waves being reflected from a parabola. Circular waves reflected from a parabola. From the focal point of a parabola, the reflection is a plane wave. Observe the differences in the reflections as the source is moved. The source is being moved toward the center of the semicircle. Observe the differences in the reflected waves as the source gets near the center. The source is moved to the center. Notice the reinforcement upon reflection. Observe the reflected waves when the source is beyond the center. A plane wave converges at the focal point of the parabola. The plane wave train converges at the focal point of the parabola. The wavelength ratio equals the speed ratio. The 45-degree waves are bent toward the normal. The 55-degree waves are bent toward the normal. The wavelength ratio equals the speed ratio. The 20-degree waves are bent away from the normal. The 30-degree waves are bent away from the normal. The 35-degree waves are bent away from the normal. The 50-degree waves are bent away from the normal. The 60-degree waves are bent away from the normal. These waves are reflected at the boundary. The double crest moves along a perpendicular bisector. Adding two pulses. The motion of the double crest is shown. Double crests moving. If two waves arrive at a location completely out of phase, the result is a node. Constructive interference regions are labeled by path differences. The ratio of source separation to wavelength determines the nodal patterns. The doubled source separation decreases the nodal separations. When the wavelength is doubled, the pattern returns to a previous shape. The distance between the sources remains constant. As the wavelength is decreased continuously, the angle between the nodal lines decreases, and more nodal lines appear on the screen. The slit width approximates a wavelength. The wavelength is smaller than the slit. For a wider slit, diffraction decreases. For a much wider slit, even less diffraction. The waves diffract around the barrier. The shorter waves diffract less around the barrier. The shortest waves diffract even less around the barrier. The shortest waves diffract least around an obstacle. The longer waves diffract more around an obstacle. The longest waves diffract most around an obstacle. Double slit and double point source patterns. A double slit diffraction pattern. A triple slit diffraction pattern. A 4-slit diffraction pattern. An 8-slit diffraction pattern. The diffracted waves move in certain directions. A long wavelength 8-slit diffraction pattern. A short wavelength 8-slit diffraction pattern.
The presence of ripples and then waves means energy has been transferred from the wind to the water. The size of the wave is determined by the wind's speed, distance, and duration. The wave of energy moves through the water, but the water itself only moves up and down, rising and falling in small circles as the wave passes by. Now the action of the water changes and it moves forward. At the crest of the wave, the water rushes shoreward, and on the face of the wave, it rises toward the crest. It's this action of a breaking wave that allows surfers to surf.
If you stay on an angle sliding away from the break, you never get to the bottom because you're sliding down at the same speed the water's going up.
The wave moving out from a stationary source travels equally in all directions. Notice how the wave fronts appear to pile up in front of the moving source and seem to spread out on the back side of the source. For a source moving much, much slower than the waves in front of the source are only slightly more compact than those behind the source. On the front side of the moving source, the waves are closer together. On the back side of the moving source, they are farther apart. The speed of the source is about 3/4 of the speed of the wave. Notice how the waves are beginning to stack up on the front side of the source. The source is traveling at 95% of the speed of the wave. Notice the buildup of a front of waves on the forward side of the source. The source is now moving at 105% of the wave speed. Notice the buildup and motion of a shock wave. The shock wave moves off at an angle determined by the speeds of the source and of the wave. A shock wave moves out from the source. Draw a circle around the source. You can use the angle of shock wave motion to compute the ratio of the source and wave speeds.
A mirror in the lower left corner of the aquarium rotates, so the reflected ray emerges from the water. The light is reflected back. Light always travels along reversible paths. Once the critical angle is exceeded, the ray is totally internally reflected. The internally reflected ray obeys the law of reflection for different angles of incidence.
The appearance of the girl on the edge of the pool looks normal because the cameraman is looking up nearly perpendicular to the surface. As he moves away, the angle of incidence at the water surface increases. We see her feet below the water, an upside-down pair of feet just above her real feet, and her body separating from her feet. Notice that what you see depends on your location along the bottom of the pool. As the cameraman moves away from the edge of the pool, total internal reflection occurs. This is what produces the image of the upside-down feet above the water surface. From underwater, we see her upper body appearing to be